Greetings and welcome to week 5, unit 5, simulation and instruction. In the earlier unit, we understood instruction through design thinking. In this unit, we will try to understand the simulation approach to instruction, which has become very powerful instruction tool at present. So, what is simulation? A simulation is an animated model that mimics the operation of an existing or proposed system. It is an animated model of whatever you want to study. Modeling and simulation refer to a combination of processes in which a system's behavior is demonstrated or predicted by reductive computational representation. That is, you are mathematically modeling something. Whenever you model, you are always creating a simplified version. Sometimes, for certain purposes, you oversimplify. Sometimes you add more features and the corresponding model may become more complex. But in any case, any model that you create is a simplified version of the actual physical process. Okay. So, what we are doing is we are trying to study the behavior of a system using a simplified model of the process. So, to that extent, one should remember that whatever you are understanding is only a limited version of what the actual process is. Now, whether it is adequate or not is to be decided later, but you have to acknowledge that it is for example, we make something that is very nonlinear. I will create a linear model for that and simulate it and look at the results, and I should know when I have simplified like that to what extent my results are applicable in real life situation. Okay, that's what it means. Modeling and simulation processes are highly interrelated and at times are used interchangeably, because you are constantly you are looking at the physical process and going into an abstract world where you have mathematical representations of that under some assumptions, and then you are working with that. So, when used in educational context, modeling and simulation skills and tools can further support the integration of both what we call divergent and convergent thinking. And in addition, we have W5U5 of the MBA, which all graduating engineers will have to attain. What does W5U5 say? Modern tool usage, create, select and apply appropriate techniques, resources and modern engineering and IT tools, including prediction and modeling to complex engineering activities with an understanding of the limitations. So, all features of simulation are really expressed here. So, simulation constitutes one of the modern tools to understand and design complex engineering products and systems. Now, sometimes the tools can be simple, sometimes they can be very complex. It takes a lot of time to master the tools effectively to make use of it, and it is also possible by not using the tool appropriately, your simulation results may represent something wrong. That also one needs to ensure that your simulation is correct. You will see when you go to complex systems where people are involved, one can make a mistake, one can make errors in modeling itself. Okay. There are any number of open source and proprietary simulation tools available for all needs and occasions as of today, and people are continuously creating more tools. Many simulation tools have good presentation and visualization features. That is, we appreciate something better when it is presented visually in 2 dimensions or 3 dimensions. And that makes learning experience a lot more meaningful and even immersive, because you constantly manipulate some parameter to see how the animation is changing. Attainment of W5 is of concern to all faculty. Attainment of W5 needs to be integrated into the curriculum. One way to do it, a course on modeling and simulation can be designed as a core course. One may may have a different opinion on that, but that is one way of meeting W5 by having a course on modeling and simulation. It can correspond to your particular branch as well. Or the other choice is simulation can be integrated into several courses in science, engineering science, and engineering courses. This is already being done in several programs. People use simulation tools in some of their courses. But the thing, it has to be demonstrated while doing the instruction in the class. Then there is a still more complex one. Simulation is the approach to study complex engineering systems, when the systems are complex, whose study is a requirement of MBA. Because if you look at complex engineering systems or complex engineering problems is repeatedly mentioned by MBA in their POs. So it is practically required that you have to use possibly simulation is the only method of understanding complex engineering systems. And some of them are likely to have people and machines besides physical elements. So when that becomes, you have no choice other than exploring through simulation. Let's say course on modeling and simulation. If you have some suggested sample course outcomes, you don't have to agree with that, but this is a suggested one. Develop mathematical models for engineering systems using fundamental principles and domain knowledge. This is PO1 and PO2. Simulate physical systems using tools such as MATLAB, Simulink, ANSYS or COMSOL and interpret simulation results. This is PO2 and PO5. Validate simulation models with experimental data or benchmarks, identifying sources of error and uncertainty. That should always be part of a course on simulation, PO2 and PO4. Analyze the performance of a model systems under various boundary and initial conditions and propose design improvements. That addresses PO2 and PO5. This is particularly important because when you have modeled, you are modeling under, there are some boundary conditions associated with that. And if you are trying to simulate beyond the boundary conditions, you may get all kinds of funny results as well. It has been shown that you get 100% wrong results. So one has to be careful, and the student needs to be exposed where you are going beyond the boundary and or initial conditions as well. Communicate modeling methodology, assumptions, results and recommendations effectively through technical reports and presentations. That is PO9. Okay. Modern engineering workplaces commonly use modeling and simulation tools to aid analysis and design of systems. For example, if you are an electronics engineer working in a company that designs VLSI, and their practically day-to-day job is to use a simulation tool whenever you make a design change. If you want to find out what is its impact, the only mechanism you have is simulation. Modeling and simulation skills have been integrated across many science and engineering disciplines as analytic tools. These tools support the study of complex phenomena and as predictive tools that can anticipate the suitability of new designs. This is what people who are involved in design in any branch of engineering, they constantly work with that. Simulation offers a powerful evidence-based approach to decision making by using a virtual representation to test the impact of process changes and what if scenarios. You can find an approach that delivers the best results. The interesting part is what if scenario. If I change like this, if I give a different input, if I use a different material, if I change a parameter, what is likely to happen? That way I can understand the nature of the system much better, provided my modeling is appropriate. And a survey of industry expectations, if you see, the industry expects graduates should be able to characterize and solve problems at the operational and conceptual levels, translating between physical and virtual world. Once you model, you are entering a virtual world. And if something that you produce from simulation in the virtual world, and if you bring it back, something is not right, again you have to come back to physical world and try to see what is happening and modify your models. So this constant ability to constantly shift from physical world to virtual world is a requirement as expected by the industry. You manage, will collect, store and secure data, draw meaning from information and communicate that information to others in a meaningful way. This is a requirement by the industry. Learn multiple software and computational systems. Use information technology, collaborative tools, instant messaging and AI to increase business productivity. People don't expect for you to spend an enormous amount of time continuously learning. You should learn and use all these tools to improve the productivity. Now let us come to next level, namely simulation in courses. So you have static models. What happens? Have an input-output relationship given in the form of some equation. But by having equation, I may not have the feel for it. So to have the feel, if I can plot in using some tool for different parameters in the equation, then I get a much better feel about what I am working with. For example, what you call Chebyshev or an equiripple function can approximate a box-like behavior of a filter. Ideally, filter should have a box type of input-output relationships, frequency versus the output. And as you cannot, it is ideally impossible to have a box-like structure, you approximate it. There are any number of approximations to that. One is Chebyshev polynomial, and the equation looks like this. And here K1, K2 are the parameters, and omega is a normalized frequency. And what you do to understand the behavior, what happens when I change the parameter, I can use a tool like graph to plot the input-output, frequency versus magnitude curves like that. Then I know I can easily appreciate the role of the parameters which are K1 and K2. Okay. I don't have to work out the details of these changes here, but this is the way a teacher can present in the classroom. Now we have in engineering, obviously you not only have static systems, you have dynamic systems. A dynamic system consists of several dynamic elements or subsystems interconnected in open loop or closed loop mode. You have several of these, and mathematical models of dynamic elements are developed first, and then they can be interconnected to create the system under consideration, and simulation software like MATLAB or Scilab can be used to simulate and study the behavior of dynamic systems. Both the software tools have very good visualization features as well. Of course, in case of electronics, you can use MATLAB or Scilab, but you can also use other tools like PSpice and so on. When the system under consideration has multiple feedback loops, it is difficult to develop a feel for the system behavior without using simulation. You can't just write equations and say you now understand the system like that. And you have domain specific tools here. As I mentioned, SPICE based software tools like MicroCap, TINA, TI are used for study and design of electronic circuits. Bond graph is an explicit graphical tool for capturing the common energy structure of systems. This modeling technique is used in studying power hydraulics, mechatronics, general thermodynamic systems, electronics and non-energetic systems like economics and queuing theory. You can create a bond graph where elements of all these areas are put together, and that is the advantage of bond graph. And here TSAT, Thermal Systems Analysis Toolbox, an open source software, is a graphical thermal systems modeling and simulation package built in MATLAB Simulink. So it's if you use this toolbox, you can simulate thermal systems. But if you are more complex, you have a commercial software like Flowtherm, ANSYS, Abacus and other tools. Now, this is a frequency locked loop simulated in TINA TI, which can have the operational amplifiers and several devices, several other hardware devices. They can all be put together like this, the circuit, and you can manipulate, you can understand the behavior of frequency locked loop. You can change different parameters and also look at the behavior of different elements as well by looking at the output at selected points. This is a wonderful tool to study frequency locked loops. Simulation of real life processes, if simulation can be visual and animated, allowing you to easily see what is happening in a process as time progresses. It can be interactive, so you can quickly adapt it in any way that you might consider changing the real life process. Another feature of simulation is you can simulate events that take place sometimes years, days, hours, seconds, minutes and so on, and depending on the complexity of the situation, you can simulate in a much shorter time as well. So it can be compressed. The time can be real time can be compressed into small time. Whereas the other way can also happen, like in electronic circuits, microsecond events can also take several hours to days to simulate something. Okay, one should be aware of that. Simulation allows you to compare different configurations under the same conditions. You can explore various alternative configurations, structures. There is one intuitive simulation software called as Simul8. Using intuitive simulation software, one can build a visual markup of a process like creating a flowchart. Like flowchart, there are library of elements, you can drag and drop and connect one to the other, and these are all already pre-modeled, and you can quickly create a system using this pre-modeled, and where the interfaces are also taken care of, and using a drag and drop method. And maybe it works quite well to initially come with some configuration. Then you can look at the details, whether a particular model that you have used is satisfactory or not, that you need to modify, but that can be a second step. But using such intuitive simulation software can speed up the initial stages. Now coming to a system, we are interested in simulating complex systems as well, right? What is a system? A system is a group of interacting and interconnected entities, objects and or people, organisms that form a unified whole. Let's say you want to simulate what happens in a electric grid where people are consuming, coming on to the system and coming out by switching off and so on. And if you want to study that, you need to understand the behavior of the people, and you should be able to simulate. A system is delineated by its spatial and temporal boundaries. But you cannot simulate everything in all its real life forms. You have to make assumptions and draw boundaries, and both temporal and spatial, before you simulate. So once you draw a boundary around something, you have to look at what happens at the boundary. What is the environment that is influencing, and what is the output of this subsystem or the system you are concerned with on the environment. You would like to look at both. So the engineering systems include, for examples, electric and electronic circuits, that is very specific, a civil structure, an engine, an aircraft. Aircraft is an assemblage of enormously large number of physical, dynamic, chemical and so on elements, electrical, electronic subsystems. A factory, a power station, an electric power grid, an engineering college can also be simulated. It will be interesting if someone can simulate an affiliated non-autonomous college, how it functions with all its management. It would be an interesting exercise to simulate the behavior of that. But first of all, you have to find out what behavior are you looking for, and do you want to develop a model of that, how decisions can be made or should be made. So it depends on what you are looking for, and even a corporate can be modeled. Okay, some systems consist only of physical elements, some will have persons and machines as a part of that. People in the system, if you want to have such a situation, it also becomes necessary to model systems for decision making, policy design and business. All of them need to have that. So if you are looking at a business model, you require to model with respect to some variables. Then if you are trying to look for policy design, you have to look for a different set of variables and so on. like tools like Swarm, Mason, Repass, StarLogo, NetLogo, OBS, Agent Sheets, and AnyLogic are tools for agent-based modeling and simulation. And analytic hierarchy process, AHP-based tool, is for decision making. It's called expert software, but it can be used. Vensim is a tool for simulating business societal dynamic systems. It uses participatory modeling. The people involved in that are participating in actually creating the model. It facilitates modeling system consisting of multiple decision makers. That is the interesting part. When you are looking at even a factory, there are different decision makers in that. When each decision maker is trying to optimize the behavior of his subsystem, the overall system may lose. So if you want to study that, Vensim is an excellent software tool that enables people to work with one another, actually participate dynamically. Okay, put all the decision makers in one group and make them explore various alternatives. Virtual reality and gaming are also effective in studying systems with people. Okay, so you have gradations in system software. Even like Vensim type of tool also can be brought into undergraduate program depending on the kind of curriculum that you have. Here you have two things. When you go out, when you graduate, you are working with a customer. Graduate students are working with customers. In such a case, one of the things graduating students should remember, you have to define what constitutes success when you have a simulation project. You must have clarity from your side, and it is also necessary to be aware of that the two parties are likely to have different views of what constitutes successful simulation project. Customer may have one view, you may have one view. So it is necessary that you have clarity first at the beginning, but as the project progresses, the customer may change his expectation, or the designer may also want to redefine his success. So the definition of success is not simply binary variable, but it can vary considerably throughout the life of the project. So the engineer should be conscious of this when interacting with that. It is not specification or definition of success is not rigid or fixed. But in such a case, what should the teacher do? Instructors can effectively make use of simulation tools appropriate to his or her course. That some people are doing. It depends on the resources available as well. Demonstration of the behavior of the system using simulation before modeling and explaining the underlying concepts and procedures is greatly motivating the students. You take something like, even if you are teaching, let us say, what do you call, frequency locked loop. You don't explain the theory of that first. You kind of simulate and show first how it behaves, what are all the parameters associated, and then come and explain the theory. That is more motivating to students than doing the other way around. Okay. What if simulation of the system under consideration greatly facilitates understanding? Open source and student versions of simulation tools can readily be used. Teachers must make special effort to learn and master the simulation tools they would like to use. And I can tell you that simulation can if you use effectively in the classroom, it can motivate the students to learn, and that too, and deepen the level of engaging with the particular topic. Okay. In the next week, we will try to understand instruction for metacognition, critical thinking, understanding, and working and writing to learn. And thank you for your attention.